Also, second apology, I suppose I feel a bit of a fraud here because, unlike David, I am not a well-known educator, although I've been teaching for 44 years. I regard myself as an indifferent lecturer and teacher, and I think my students would probably agree. So I feel that I should really be learning from you rather than the other way around. But I will, if I can stimulate some discussion, I will perhaps have done some good here. The third I suppose, apology is that I ought to have coordinated with my friends and colleagues, David and Barbara, and have not done so. So there's a certain amount of overlap. But what I may have a slightly different take here, and I think what I ultimately want to get onto, and this is perhaps sort of starting off or triggering some things, is to think a little bit more, which I think was what I was asked to do, and I'm not totally sure I've got this right, but to concentrate more on how to actually use the material of modern astronomy and astrophysics to communicate physics ideas to essentially undergraduate majors, particularly concentrating on the first and second years. And so I'll say a little bit about that. Charles mentioned New Worlds, New Horizons, and this is the cover of the report that we created. I'm certainly not going to go through it here. I've given about 25 talks already on it, and I certainly don't want to give a 26th. But I will just list these as the three science themes that emerged from it. And these, and I think, despite budgetary problems in the United States, these probably are still a very good guess as to where the action is going to be and what your students are going to be hearing about by reading popular articles and so on. The first is what we call cosmic dawn, and this is sometimes called technically the epoch of reionization, when the atoms in the expanding universe are then separated again. Quite sure why it's called reionization. They weren't ionized before that, but they did. It's soon after then is when the first galaxies and stars were formed, and so we are at some level starting to glimpse that area using astronomical telescopes. We're also seeing the fossil relics of that time in very, very old stars. And this is understanding actually what happened and when and where is one of the great challenges of contemporary astronomy, astrophysics, and cosmology. The second growth area is what we call new worlds, but it's really concerned with the discovery of exoplanets big time. Now, I'll come and say a bit more about this, but the extraordinary thing has been how diverse they are and how common they are. And my own view is that we're actually at the start of this epoch of discovery, not even so. I think it really is quite amazing how developments in techniques that have effectively been around forever but not terribly efficiently used, a lot of them very inexpensive, have led to this great flowering of a completely new field. It's attracted a lot of young people. Many of the best graduate students out of astronomy and astrophysics departments are headed for this area. It's a very different type of science from the cosmology and the high-energy astrophysics that attracted their predecessors, involving chemistry, biology at some level, certainly old-fashioned celestial mechanics, but they're very new guys, and so on. And then the third type, which is still, again, very active, and again, we're seeing the pursuit of doing physics, which is perhaps what we're more concerned with in this meeting, using the universe as a giant laboratory, not one where we hope to perform experiments, but one where we allow the universe to perform the experiments for us and we take the data. And the big topics here are, of course, dark matter and dark energy. I'll say a little bit about this. Inflation, I would say not so much about it. I think it's a little bit hard Well, actually, I say a little bit about it, and then general relativity, which I think you can do something about in this, this target group of, first 2 years of undergraduates, perhaps, who are taking physics. Oh, here we are. Yeah. So, one of the great attractions of astronomy, you've just seen this spectacularly demonstrated by David, and you will see, I think, by Barbara, because she's like, and I'm not going to belabor this. This is just a throwing down images from all over the place. They're just random set of them. It's something that astronomy has, which catches the public imagination. So this is more the sort of, if you like, the lost leader for people, getting people interested in science. And astronomy has this great advantage in that this appeals not only to the topics we're dealing with, but also the images that we can create with our telescopes are sort of riveting, and they do bring people in. And we should not be ashamed of that. We should use that all the time. I think there's a second, and because I think it's the case, David may know the answer to this question, that I think it's something like 250,000 students do some form of astronomy as their sort of, this is the science that they get. It's the most popular one to take. And so we have a golden opportunity for teaching something that I might say is in somewhat short supply at the moment, which is critical thinking. Now, it's not the same as teaching experimental science in the laboratory and so on, and many other types of rational thinking, if you like, but it is, I think, more relevant than just astronomy, because a lot of it's based on observation. Increasingly, one's dealing with sort of social issues or political issues and so on, where you can't perform these great experiments. You can't take some sort of medium-sized country and willingly send a lot of people, white-coated economists in to completely say, well, I wonder what happens if we have no taxes, or I wonder what happens if we have 10 times the taxes, I wonder what happens, you don't do that sort of thing, or climate change. I wonder what would happen if we inject vast quantities of aerosols into the atmosphere. What will happen? It's a good experiment to perform, life as we know it may end, but it's a good experiment to perform. You don't do that sort of thing, so you're doing much more observational and inferential things. And we have, I just picked 3 out of anywhere that we could use, but we can use these as sort of case studies for how astronomers methodologically attack this type of problem, which might have some relevance to other problems that are way outside astronomy, where you really want to know what will happen if, and then you have to sort of assemble the evidence you have without being able to perform the experiment that one part of your brain might like to perform. Another thing that I like to say is when we're teaching, and this is certainly my experience, when we're teaching the first 2 years or so of astronomy, one is very more often than not teaching engineers than people who will end up as pure physicists. And the mindset of an engineer, as a professional or as a student, is already somewhat divergent from our view of what physicists are. Not in a bad way. My own 2 sons are both professional engineers, and I'm very proud of them, and they're very suspicious of physicists, in good cause. I certainly brought them up that way, and but I would say that what they're more concerned with is really rather different than the sort of traditional concerns of the physics professor. And so you might sort of say, well, the engineer versus physicist is the experiment versus theory. The physicist is interested in theory, and the engineer doesn't really care whether those kind of functions will make something work. Well, that's sort of right, but I think the really integrating experience here, and this is where physicists and engineers can come together on, I think it is in the undergraduate research experiment. It's not doing the carefully constructed experiment in the first year physics laboratory. It's really doing the discovering either research or development in some undergraduate research experiment when you're dealing with things where you don't know what you're doing. The normal state of grace is it doesn't work. And the person who's giving you an advice didn't know what they were talking about, and so on and so forth. And this is, I think, an integrating experience for engineers and physicists. And then, as I said, the implementation versus the versus principles. I mean, you know, the physicists might have a view of engineers that would say, well, all they're interested is looking it up in some table somewhere. They don't care about it at all. But that's not good engineering. I think any engineer will say that too. You've got to understand at a very fundamental level, because that is more often than not the pathway to innovation nowadays. It might be in the past you just stumbled on something by pure chance, and that we're waking up to know this, but more often than not, it's through understanding is the route to innovation. And innovation is what a lot of engineering should be about. I think there's another sort of axis here, which is the integrative approach versus the reductionist approach. Physicists, certain types of physicists, are famously categorized as being reductionists, as they used to call it nothing buttery. So you're always trying to reduce things to the most fundamental element and so on. Now we all know as physicists that that is not a fair characterization of even modern physics, even modern theoretical physics, because a lot of it is many-body, is collective, and so on. And so it is not reductionist. And the engineers, certainly for them, it is the system that is very often the important thing. And I think, again, that can inform our teaching. Another sort of axis that I think is important and worth thinking about is specialism versus generalism. Engineers quite often are quite specialized. They'll decide, one of my sons did, it's very early, starting off, well, he's going to be a mechanical engineer, so he's a mechanical engineer, you know, and so that's what they do. So doesn't know anything at all. So it's that to some extent that's true, but if you look at an engineer trying to make something work, trying to build something, it's the failures that are important and interesting, and more often than not, when things go wrong, which happens a lot, of course, it's because there was something that wasn't in the rule book, in the pathway, something outside you didn't know about. And here, I think it's very important when teaching engineers, and I've certainly been told this a lot by engineers, it's something that physicists are doing more of now, but I think it's even more important for engineers, is for understanding sort of back of envelope, order of magnitude type of analysis, so that you can deal with some design or some critical or some system or something like that, and you can make quick estimates that will tell you, well, I don't have to worry about that, or whoops, I didn't really expect that to be important, but if I believe this estimate, it's a 10% effect, so I better go back and look at it in a bit more detail, I better learn a bit more about it. And the failure to carry out that sort of analysis is quite often, it's one of the two major failure modes that happen. The other, of course, is the interface between two groups that are not talking to one another. And then finally, now I'll finish up with this, is the notion of how important is computation versus analysis. Again, the traditional physicist does these elegant calculations using 19th century applied mathematics and so on. And for an engineer, a lot of that has gone out the window, because even more than physicists, they are reliant upon computer-aided design, numerical simulation, and the rest. This is the professional life nowadays. And yet the analysis does have an importance. And I think we have a responsibility to keep that there, not at the level of the very intricate problems that people used to solve because they didn't have computers, but at the level of being able to convey understanding by having a good suite of work problems that represent a sort of lingua franca of people trained in physics and engineering. So everybody they've done that problem once before, and they sort of know it, and it provides a sort of reference point for a much more complicated analysis that might involve some finite difference numerical simulation or whatever. So those are sort of very general remarks. I put these in and I was going to take them out clearly because I think David's probably done this, but let me just sort of make some, I think David made these points very clearly. The visible spectrum is just one measly octave, and many of my colleagues are optical astronomers, and they have, I think, a very jumped up view of their own importance. So you know what this means. So there's the electromagnets, there's 10 grand piano's worth. Sorry, I didn't realize I put all this stuff in here, sorry, I apologise. So they're just there, that one octave there, you know. And so here's, you know, I'm sort of a gamma ray astronomer some of the time, and we have 4 grand pianos worth for that one octave for the ultra astronomers. And of course, if you go to the other parts of the spectrum, you go into the cosmic rays. We're going, I'll make this point in a moment, but they go up to zeta electron volts. So that's way beyond the electromagnetic spectrum that we're doing in astronomy. And then in neutrinos, dark matter, and gravitational radiation was there. Okay, it was gravitational radiation was there. So that's down here. So we have these 4 non-electromagnetic channels too, with another 70 octaves worth of spectrum there. So this is opening this up using technology is the reason why there's been this explosion in astrophysics over the last 50 years. Okay, so let's talk about some of the topics that come up. And I might be riding some hobby horses here, so which I apologize, but let's try and discuss some of the concepts that may come across and where astronomy and astrophysics, cosmology, so on, might have something to contribute to getting the ideas across to a student that's trying to learn the subject. So, I have some background in relativity, so geometry is always very important for me. And, of course, the classic question was, Euclid's fifth postulate and all of that, is space actually flat? To Kant, this was an a priori truth. For Gauss, it was not a truth, because he sort of knew about non-Euclidean geometry and so on, as did others. And he performed the experiment. I think there it is. The experiment when he didn't do it, he sent people off. He was an observatory director at that time, so he just sent other people off to do it. To see if the angles in a triangle added up to 180 degrees. It was a good question, within the errors it did. If you ask about the universe at large, as investigated by cosmologists, I would think that most theorists, before the 1980s, had a suspicion that the universe was not flat and you had to use non-Euclidean geometry to describe the space of the universe. After the 1980s and the postulation of the theory of inflation, there was a reason, not actually accepted by all theorists, but by most, I would say, for believing that the universe was a mechanism for flattening out the universe. And so a lot of theorists would then have said that the universe is flat and the angles in a big cosmic triangle would add up to 180 degrees. But the observers were rightly suspicious of all of these arguments and went off and, to all intents and purposes, used the microwave background to measure it. And to a fraction of a percent, we know that it appears to be flat. So this is something that I think is sort of, it's an assumption, but it's not too soon in an undergraduate physics course to explain, just as you do in mathematics, that this is something for which we have some basis for believing, and the world didn't obviously have to be like that. One thinks about kinematics and so on. Again, when one goes on, you get students from high school who are well armed with techniques for solving problems in dynamics. It's up to a point. But it's very important to go back and re-examine the kinematic foundations of what you're doing, what you mean by time and space and length and dimension and so on. And it's not just a question of the idea of what is meant by length and why time is different, or is it, and so on. It is really expanding the student's view of these quantities, of these physical quantities. In astronomy, they've probably heard of Planck's constant out of high school. From dimensional analysis, you can create the Planck length, 10 to the minus 33 centimeters or thereabouts, from the Planck time, related to that obviously by the speed of light, use the 15 denominator and so on, 10 to the minus 44 seconds. You sort of know this. It kind of blows the mind a bit, blows my mind a little bit. On the other end of the scale, if we just look at the characteristic size of the observed universe, the Hubble length is 10 to the 28 centimeters. The characteristic time is 10 gigayears. We're clearly doing order of magnitude analysis here. They will have read in Scientific American or other popular articles or whatever about the landscape and the multiverse and how this can go, that we can live in the eternal universe in this way, continually putting on new forms and so on. And the characteristic scales are 10 to the 10 to the 10 to the 10 to the 10. And if you want to know what units I'm using, you're kind of missing the point. And so this is an enormous range of scales here. And I think just understanding these relative scales is important. From the point of view of astronomy, we're now at the point where we can communicate, I hope, a familiarity with the observed universe. I'm not going to go on into the multiverse or anything. And just as one can say that, you know, I'm 10 billion atoms tall or something, and another 10 to the 5th protons, you know, stack up one on the other, I can get some scale going to the bottom. Going to the top, one can develop an appreciation of the relative length scales involved. So in the very roundest numbers, you would like to communicate, and there are different ways of defining this more precisely and all the rest of it. The universe is roughly about 1,000 times the separation of big galaxies, and 1,000,000 times the size of a galaxy, and about 1,000,000,000 times the separation of stars, and about 10 to the 12th time the size of a solar system. And I didn't know how big our solar system is, so I took the geometrical mean of the Kuiper belt and the Oort cloud. And then about 10 to the 15 times the Earth orbit. You know, I'm not saying there's a quiz in which you have to write down these numbers, but to have some appreciation that isn't just very big, it's, you know, millions, billions, trillions, we should be able to have some sense of what those are in comparison. In terms of time, now take the age of the universe now, it's 30 times the age when the first galaxies and stars started to appear. 30,000 times the time when we see the microwave background, and so on. This sort of relative thing is important. And the physics, one of the physics points here, I think, is that with one or two exceptions where there are genuine questions to ask, so far as we can tell, the sort of physics that we divine from laboratory experiments, from looking at textbooks or whatever it is that are very much sort of terrestrial based, applies on these different scales. There are some people who will just question what I've said, and there are one or two places which I may come to where there are good grounds for doing that. But mostly the physics that we use seems to apply on these very much larger scales. The transitions for atomic lines and so on appears, different ratios and so on, the same in a distant quasar as they are in some incandescent bulb in the laboratory. Speeds. Again, this is sort of just relative, just trying to put things in perspective. The sprinter here, I'm not sure I can do this, but does about 10 meters a second. The speed of sound about 300 meters a second. The stars going around the galaxy, like Andromeda here, 300 kilometers a second. Dark matter particles, too, for that matter. They were talking about matter particles, they're doing the same sort of speed too. Light, of course, 300 megameters a second. To have some sort of understanding of the relative sizes of this, and astronomy is very good, I think, for conveying that. And the ultra-high energy cosmic rays, this is what I like. The highest energy cosmic rays, the ones at ZeV energy, I'll turn this a little bit at the end, lags a photon by a femtometer, a Fermi per second, or a couple kilometre per Hubble time. So a cosmic ray coming from the other side of the universe would lag the relevant photon by a kilometre. So this is just kinematics, but getting some sort of sense of that is good. This is actually fun that way as well as that way. Okay. Masses. Again, just relative sizes. Again, you don't want this to be like those dreadful middle school science tests where you have to recite the geologic eras and so on, the periodic table of the elements and all of that. Don't want that. But somehow to develop some appreciation, some familiarity. The sun's 1,000 Jupiters and nearly 1,000,000 Earths. a galaxy is 100 billion stars, and if adding the dark matter is probably nearly 10 times that in terms of stellar terms of mass. Cluster galaxies, which you've seen some from David, 1,000 galaxies. The sky, look on the sky, count up the number of points of light there. Some of these are pretty feeble galaxies. We wouldn't want, we'd be rather ashamed of them if they were, if they were our relatives. But they get grow and marry and all that. So 100 million on the sky. You just add them up. Okay. So that's something to idea. Densities. Now there's something that's very central to astrophysics. And so the little formula is that the characteristic gravitational timescale is 1 over the square root of Newton's constant times the characteristic density. And this comes up all the time. The densities, for a person, for the sun, for a planet, it's a little bit more than this, but it's roughly about 1 gram per cubic centimetre, and so on. We're mostly wet. And it's 1,000 times that of air. That's not an astronomical thing, we sort of know. If you go to a dense structure in astronomy, that would be a neutron star. It's a star, so there's 10 to the 33 grams there. A proton or nucleon is 10 to the minus 24. So there's 10 to the 57 nucleons, roughly in a neutron star. Cube root of that is 10 to the 19. Multiply that by a Fermi, the size of a nucleon, and we're up at 10 kilometers. Okay? So again, density, and the Planck density, the one that you get from the Planck mass and time and so on, is of course 10 to the 77 times that density of a neutron star. So we can certainly blow the mind away a bit by that. The universe, its average density is about 10 to the minus 4 times that of a galaxy. 10 to the minus 29 that of a person. 10 to the, I think I've made the largest mistake I think I made in my teaching career. One of 242 orders of magnitude. Even an astronomer except those working on the please take my notes, put a minus sign in there. Okay. So, as I think David alluded to, this is something that is very common, but it's sort of becoming part of culture almost now, but not really. It's worth driving this home. The baryonic matter that we, and other things that we know about are composed of, is 4.5% of the mean density of the universe. Obviously, locally, we're doing a bit better than that. The dark matter, the two mysterious components, one of them the dark matter, is about 20%, 19 to 20%, and then the remainder, almost 3/4, in terms of mass energy density, is the dark energy. Okay, two distinct components that have been identified by cosmologists. This sometimes helps to get the point across. Okay. Energies. I mean, astronomers like to watch things blow up. Maybe they like to blow them up too, especially the Rocketeers. But again, a good point to get across. Chemical energy. I mean, dynamite is something pretty fearsome and impressive. You can take out whole sides of mountains with it. It is using the bomb maker's prescription. It is 0.048 eV per nucleon, or 5 times 10 to the minus 11 c squared. Nuclear energy, as in a bomb or a reactor or a star, is in round numbers, MeV per nucleon, 10 to the minus 3 of c squared. Gravitational energy, under practical astrophysical conditions, if that's not an oxymoron, is 10 to the minus 1 c squared, 100 MeV per nucleon. So gravity power beats nuclear power with vastly overwhelming chemical power. That is something that students don't always appreciate. They think a nuclear weapon is, it's like a big stick of dynamite or something. This is a big difference. Energies. mc squared for a star, the sun is about 10 to the 54 ergs. But if you ask how much energy you get out, it's consistent with this, either as a result of nuclear reactions, either as a result of burning slowly over the lifetime a star like the Sun, or explosively in one of those supernova that David showed you, it'd be at 10 to the 51 ergs, about 10 to the minus 3 of its total rest mass. And a galaxy, typically over its lifetime, including its nucleus, in radiant energy, will produce about 10 to the 61 ergs. So these are huge numbers. Okay, so I try to organize this a little bit by physics topic, rather than by going through the astronomy, and sort of say how you might actually drag in a little bit of astronomy. It might help. It's not just a question of selling the astronomy, it's not marketing or anything. It's where I actually think that you can enlarge the student's appreciation of the actual physics content of what we're talking about. Newtonian dynamics, of course, the one does the circular orbits around the Sun, of the planets, what's left of them, and you note in very round numbers that the Saturn, it's 9 AU, the orbit, and so the period's about 27 years, and so on. But you can do much more than that, especially now. And I'd advertise especially the binary pulsars, and the reason why I advertise this is exquisitely accurate. Radio astronomers measure very, very carefully the arrival times of the pulses from pulsars, and can, with exquisite precision, measure the orbits, and indeed go on further than you need for these purposes to measure relativistic effects and so on. But when you want to go from the planet going around the Sun to the two-body orbit and the eccentric orbit rather than the circular orbit, then binary pulsars are great. Here's PSR 1913 plus 16. Its period is 8 hours, its eccentricity is 0.6, its size of the solar radius, size of the orbit, and it follows that orbit with exquisite precision. And this is quite interesting, and there's another thing that's, I think, conceptually interesting here, and that is one thinks about the Doppler shift, particularly Newtonian Doppler shift, as the way of measuring the velocity of a moving body. But the way the radio astronomers actually do it is they register the arrival times of pulses. That is kinematically equivalent to measuring the Doppler shift, but that is not obvious to a student. That's a good point to try and get across, and I think it enhances your basic understanding of these fundamental kinematics. I've waxed lyrical about the extrasolar planets. As of this morning, I think there are 563 that have got some good housekeeping certificate of approval, and there's about 2,000 extra lurking out there, most of which are probably correct. It's a reasonable presumption that there are twiddles 10 to the 22 in the universe. And if anybody asks you, it's perhaps possible that one of them exhibits more intelligence than we seem to be doing at the moment. So then range, the diversity is enormous. Earth to Jupiter's periods from days to years. Here's Gliese 581, which has been in and out of the news. I am not going to put my body between various astronomers who are or are not detecting planets, but I think it's fair to say that all of these planets are confirmed, and some of the others may well be true, but still it's pretty remarkable, this system here. And there's a red dwarf. The star in the middle is not like the Sun, it's a red dwarf. Okay. And you short orbit, so you get that good immediate gratification and so on. So you can make homework problems out of this and so on. It's much more fun than Jupiter and Saturn and all that. Okay, thermodynamics. Here's another topic. Now, the theory of stellar structure is one that has been developed from the 19th century through the 20th century with the atomic and nuclear physics that it needed, to the modern era of computation where you can compute with confidence the structure of main sequence stars, their evolution, and there are certainly some parts of this that we do not understand and cannot describe, but most of it is a glorious scientific success story. How the elements are made and so on. And a central part of this is the thermodynamics. The thermodynamic properties of ionized gas, parts that become neutral and so on, how its composition changes, and this in a sort of simplified form, is, I think, a splendid vehicle for bringing out the principles of equilibrium thermodynamics and statistical mechanics. Entropy is always a big puzzle for students as they try to get their head around what is meant by entropy. You can get quite a lot out of stars. The sun, the entropy, increases as you go outwards from the core of the star to about 70% of the solar radius, at which point it is constant because the outer parts of the sun are convective. And so all the gas gets mixed up very fast, and its entropy, because it's an adiabatic process, its entropy is effectively constant in that region. That can actually, I believe, be helpful in teaching regular thermodynamics. Another example that I actually quite like, although it's a little bit more remote, are the clusters of galaxies, where, as we're trying to understand the physical processes that happen in the gas that surrounds the galaxies that David showed you some examples of, these 1,000 galaxies in a tight cluster, the entropy there is measured by the X-ray astronomers. It increases outwards, and the very recent discoveries, it's sort of hot off the press almost, is that the entropy in the outer parts of these nearby clusters of galaxies is remarkably high. And we know from cosmology what the entropy is in most of the intergalactic medium. We know what happened to it from recombination to reionization, from the when we first see the microwave background, from where we first see the first stars and galaxies. We know what happened to the entropy. That entropy is very large, much larger in the outer parts of clusters of galaxies than it is in the intergalactic medium. How did that happen? Well, there really is only one answer, and this is what David emphasized in a slightly different context in his talk. There has to be very strong shockwave there. Again, this is, I think, a useful vehicle for getting across these ideas. Let's do another type of thermodynamics, and this is very esoteric, and it's something that is rightly very puzzling, and I think people will probably avoid this in the first few years of physics instruction, but instructors are likely to be asked about it, because you read about it in the newspapers, let alone Scientific American. And that is the dark energy. And what is this stuff? It's most of the universe, and we don't know what it is. Well, Einstein invented it at some level in 1916, called it the cosmological constant. And frankly, in spite of all of the self-important schemes of theoretical physicists to try and make it more rich and interesting, it looks like it is a cosmological constant functionally. It is stuff that is there that is universal and eternal. It doesn't change, nothing happens to it, it's just there. You can call it the fabric of space-time, but I don't know what that means, but it sounds good. You can call it vacuum energy, that doesn't make much sense, so that sounds even better. You can call it the ether, and that sounds awfully historical and getting you into rather dangerous territory. However, be my guest, you won't find anybody, it is a sort of modern ether in some sense. But if we take the view, and this is one of obviously two views you can have, that it's a stuff, it's a substance. Its thermodynamics are very simply prescribed, and physicists like to say when its pressure is equal to minus its energy density, it's constant everywhere. This is what it is. And I think the trick to try and elucidate this is to compare, for a student who at least knows a little bit, who's done a little bit of electromagnetism and knows what there's tension in magnetic field lines and there's energy density in magnetic field lines, then the pressure of a magnetic field in one of these little imaginary cylinders here with a piston coming out is going to be the tension, which is going to be minus v squared over mu naught, plus the pressure, which is plus v squared over 2 mu naught in SI units, which is minus the energy density. So just having a piston coming out in a uniform magnetic field is a very familiar thing, and this seems almost trivial. But that is the equation of state in one dimension that because it's a scalar field, we think might be appropriate to dark energy, if it's a cosmological constant. And to within certainly 10%, some would argue 5%, that is observationally, in terms of measurement, what it is. And the odd thing here, of course, and I can come back to this in a moment, is that this is this pulling, this tension, this pulling together, is paradoxically what is responsible for creating the acceleration of the universe. So let's go on to talk about this. And this is a little bit more advanced, but it doesn't have to be a lot. And again, if you pick and choose this as is appropriate for the level at which you're teaching. The cosmology of the expansion of the universe is described by what are called the Freemen Equations, after Thomas Friedman. You see, the world is funny, you got that part right. He couldn't spell his name though, there should be another N on the end. But, and this is basically what they are. Let's take the second one first. This should look like thermodynamics. This is D internal energy. I've got a box of stuff. And I'm going to say this box has a size A. And it doesn't matter what scale, everything, A will scale with everything. It just has a size A. Side, if you like. It's A. And if I say how much energy density is there in this, there's rho. That should be rho c squared. Sorry, I missed something out. That should have been rho c squared. I apologise. So d rho c squared a cubed, so that's du, and this is equal to minus p dv. Okay? So imagine a little box, that's all it is. That's the first law of thermodynamics written down. Now it may have a funny equation of state for dark energy, but that's all it is. The second equation is this. And this says that if I just imagine you and I'm here, you're a distance a away from me, the velocity with which you're measuring your kinetic energy per unit mass is a dot squared over 2, that's dA by dt squared by 2. And this, if you think about it, is I make a sphere around me, and this is the gravitational potential energy with respect to me. And so this is just Newtonian theory, and I'm saying that's constant, and you go on long enough it will be 0, etc., etc., etc. Now this is a fraud. This is thermodynamics, that's true. This is a fraud because it misses 3 key points that any student ought to be able to say, what about? First is the boundary conditions. Well, I said, you know, there's stuff around everywhere. What do I do with infinity? The second is, what about pressure? We know pressure can be big. We've just shown that. Does that contribute to the active gravitational mass? Newton didn't know about it, but we should be worried about it. And the third is curvature. This business about is the space flat or not? And those are 3 big questions which general relativity brilliantly answers. But don't shortchange the student with a sort of swindle like this. It's an easy way to remember it, but it hasn't got all the physics in. And the constant, in fact, for a flat space, and this is one of the remarkable things, is 0. You can do more with this. The energy density rho, if it's just matter without any pressure, the stuff of you and I, the stuff of dark matter, it's all cold, no pressure, nothing significant. It'll scale as 1 over a cubed. If you, at early times, it's important to include the radiation, the microwave background, and the neutrinos that go along with them. The energy density goes 1 over a to the minus 4th because the energy of each photon in the microwave background is scaling inversely with the size of the box as it expands. If we look at contemporary measurements, the matter plus the cosmological constant, then I sort of love this. Physicists sort of don't really like it quite so much. The differential equation, you can take these equations and in 2 lines show that the differential equation is the 3rd derivative of the scale factor is the cube of the velocity divided by the scale factor. So it's independent of the scale factor. It didn't matter whether I took you or somebody twice as far away as you. That's a very simple, and it's a 3rd order differential equation. So it's the jerk, one of the great physicists of contemporary life. And I think it's kind of remarkable, actually, that describes the universe. And in fact, even more remarkable, and what many students of cosmology don't actually appreciate, it has an elementary solution, which is the one that is appropriate, which is just goes to the 2/3 power of the hyperbolic sine of cosmic time, scaled appropriately. Right? That's what it is. So you make a homework problem out of this, which is pretty exciting. Okay. Let's talk about radiation. This also comes up under thermodynamics. Again, the microwave background is a spectacularly good black body. You know, people talk about some metaphorical chip of coal or something like that as a black body. Okay, 5 minutes, thank you. Okay, I'm not going to get through all of this, but I never expected. Okay, we've got stars, of course, that are good, but the microwave background is spectacular. 10 parts per million, and the deviations are things that we actually understand. It is a perfect black body. It contains the entropy of the universe. The photon, that's where the entropy lies. The scale factor increases inversely with the frequency. So the wavelength in the box will go with the size of the box. The frequency will go inversely up. The temperature, because has got a scale with the frequency. And that goes to that, and you can get everything out of that as before. So the combination, when we see this microwave background at 3,000 degrees, the universe was 1,000 times smaller than it is today, 1,000,000,000 times the density, and so on. We can use this in teaching special relativity. Here are the radiation. If you consider how to deal with radiation, astronomers are doing this all the time. There's a trick. This is slightly a higher level here, but it is a trick that you can get an awful long way with. The key thing is to use the quantity that astronomers call intensity. Don't use what physicists call intensity. Use what astronomers call intensity to define correctly. Per unit frequency, per unit solid angle. It's 2h nu cubed over c squared. This is just what Eames did, and so on, times the occupation number of a state. And this is the quantity that would be given by that for a black body, and in general is something different. It goes as nu cubed, therefore it transforms as a cubed, and so on. The frequencies transform that way. Just by focusing on the intensity is the royal road to describing how radiation gets from there to here, or equivalently and differently though, Lorentz transformation of radiation, looking at radiation in a different Lorentz frame when you do special relativity. So here again, this is the formula. All of these things go just from this simple prescription for the intensity. And this is superluminal expansion, which has found its way into many special relativity names and so on. I won't make any more of that. Very quickly, quantum mechanics. I'm just going to go through this very quickly now, just to give, we can talk about this in a bit more detail later on if you want. Obviously, spectroscopy, Fraunhofer lines, Lyman alpha is the central line from the Bohr theory of the hydrogen atom through the associated Laguerre polynomials from the Schrödinger equations and so on. Lyman alpha is the first line you come across, and of course you don't see it in the lab because it's in the ultraviolet, it's in the ultraviolet, but astronomers see it all the time, and I'm sure Barbara will be mentioning this on the shore. White dwarfs, another example of the uncertainty principle. Radio recombination lines, the correspondence principle, you're going out to n of equal to hundreds with radio frequencies and transitioning the alpha lines that transition from n to n minus 1 just have the angular frequency of the electron going around the Bohr orbit and so on. Again, but astronomers measure these things. These are something you can use to illustrate the correspondence principle. Here, sorry, white dwarfs, the degeneracy pressure, that's the Compton wavelength and so on, and an equivalent formula for the white dwarf. This can bring out the importance of degenerate electrons and the Fermi surface and so on. In condensed matter physics, similar things in neutron stars. Neutron stars essentially contain all physics with the eligible exception of string theory. Almost everything else can be found in the discussion of neutron stars, writ large and strange. So here's just some of them. Particle physics, the dark matter. Particle physics has its origin in cosmic rays. Let's just go on to that. So here we go from GeV to TeV to PeV to ZeV. That is about 100 joules up there. Well hit baseball. The energy, the momentum of a snail, that's important distinction. Particle physicists lose that sometimes, momentum and energy. They think they're the same, but regular physicists should know they're different. So, so the momentum of a snail, but the energy will work at baseball. So they're the sources of them. There's a lot going on there. General relativity, finally, black holes. I think this is show as a movie. It's the thing I hate so much, this one. It's like one of those children's tests. How many things can you find wrong with this picture? And it's shown all the time, and it's wrong in so many ways, I can't even start to tell you. However, black holes, they exist. They are simple. They're like elementary particles. They're just characterized, as far as astronomy is concerned, by mass, which is a scale, and something that measures the angular frequency or the spin. That's it. They satisfy conservation laws. Energy, mass, angular momentum, all the things that you know from regular Newtonian physics goes over to discussing black holes. The physics is known in a curved space-time. We can do any physics we can solve in a practical context, in a flat space, we can solve in principle in a curved black hole. And they're terribly important to astronomy because they pack quasars, gamma ray bursts, and so on. Let me just finish. This is something I was going to say a bit more about, was numerical simulation. Astrophysicists have embraced this, particularly in cosmology. I'll show you one from black holes. This is a very recent one with my colleague and collaborator, Jonathan McKinney. And this is a blue hole here, actually, it's in the dimension. Oh no, there's the black hole. There you go. There's the black hole. And these are the jets that David referred to somewhat pejoratively. They're coming out of the black hole. And what you can see here, this is a simulation. These are magnetic field lines. This is a possible explanation for how those jets that he showed you are being produced. But what is remarkable about this is this shows in the numerical simulation, something that's been conjectured for a while, that you could actually take the spin energy of the black hole, reduce its mass, slow it down, just like we do with the pulsar, slow it down, and it powers these jets and the winds. This is the jet and these are the winds. So it actually powers them, and you are actually in this simulation leaving the black hole with much less mass. So let me finish at this point, and hope I've been able to convey a little bit of the few of the possibilities that one can use to bring astronomy into a sort of standard physics education, and maybe we can talk about a little bit of these afterwards. Thank you very much indeed.